Okay, let's do one more. This time we're going to do one that has a rational power. So we're going to find all this information, but this time we're going to do local, and they also want any absolute extrema if it has it. So first thing we want to do is find the critical numbers. We've got to find the derivative. Now looking at this, it looks as if we may have to use a product rule here. However, you don't have to. Another way to do this is you could distribute and you can use the power rule. So let's do it that method. First thing, we're not going to do any derivative, we're just going to distribute. So when I distribute this, I get 3x. I'm going to add the powers, 2/3 plus 1, 5/3. Okay, so 3x to the 5/3 and then minus 12x to the 2/3. Okay, so now we've done the first step, distributing. We're now ready to do the power rule. So when we do that, 3 stays there, the 5/3 will come down. Subtract 1 from the power, 5/3 minus 3/3. Get back to 2/3 again. This we have a minus 12, 2/3 comes down, x. Got to subtract 1 from the power, 2/3 minus 3/3 will give you negative 1/3. Let's rewrite this. Okay, so 3 over 3, we can simplify that, 5x to the 2/3. And then this will give us minus 8, but I'm going to write it this way. I'm going to write minus 8 over x to the 1/3, and the reason why is because we need to see if we have a fraction here, because remember, when we're finding critical numbers, one of the ways of doing that is finding any place where the derivative is undefined. We notice by writing it this way that the derivative is undefined at the x value of 0. However, if you put 0 into the original one, it is defined. So because of that, we do get a critical number here because of that first reason. So critical number, first one we're going to have is 0. It's very important that we remember to do this step. It's not just setting it equal to 0. Also, you got to look for where the derivative is undefined. Now we found that critical number, we are going to set it equal to 0. So 0 equals 5x to the 2/3 minus 8 over x to the 1/3. Best way to do this is to move one of the terms over and then cross multiply. We could do some factoring, but that's going to be more complicated. So we're going to move one of the terms over. 8 over x to the 1/3 will equal 5x to the 2/3 over 1. We're going to cross multiply each of these. So when we multiply these, I get a 5, and then the x, if I take the powers and add them together, 1/3 and 2/3, I'll get a power of 1. So I just get 5x. That's going to equal 8. If I divide both sides by 5, then I get my other critical number. It's going to be 8/5. So I get 0 and 8/5 as, let me make this more legible here, 0 and 8/5 we get as our two critical numbers. The next thing we want to do is put these onto our table, and then we need to look for increasing, decreasing, and the local extrema there. Okay, so we'll put this on a number line. Got 0 and 8/5 here. Make sure you pick the correct test numbers for each. Now notice that these are open-ended. There's no number on the end that's closed that causes it to be a closed domain like some of the other problems we've seen. This one, the domain would be any kind of number we can put in there. So basically we don't have any restrictions on the ends. So I can pick any number that's less than 0. I'm going to use -1. 8/5, the decimal for that is 1.6. So I can use a 1 here, and then I can use a 2. So the most important thing is making sure you choose the correct numbers that fall in your intervals. These numbers you want to put into your derivative function. This is our derivative right here, this right hand side. So you put -1 into here. If it's a positive number, you put plus. If it's negative, you put a negative. If you put -1 in here, you're going to get a positive number. If you put a 1 inside here, 1 to anything is 1, 5 minus 8, you'll get a negative there. And if you put 2 in there, you'll also get a plus. So that would be your sign configuration for working with the derivative. Now that we have this, we can write the intervals of increasing and decreasing. Remember, increasing is wherever you have pluses on your number line. Decreasing is going to be negative. So first, let's start with the increasing intervals. This is going to go all the way down from -infinity down to 0. Remember, don't use -1. It goes all the way down to -infinity to 0, and then from 8/5, not 2, 8/5 to infinity there. That's the regions that are plus. Let's now look at decreasing. Decreasing is any place you have a negative sign in the middle. So between 0 and 8/5, it's going to be decreasing. You have a minus sign there. So that's the first thing they're asking for. Next, let's take a look at the local min and local max. We're going to use our first derivative test for this one. So if you look at your sign configuration here, if you have a plus going to a minus, that means that you're going to have a relative max at 0. So we're going to do relative. We can do relative or local. Again, doesn't really matter. You can use both of those. We'll use relative max. That's going to occur at 0. The relative or local min is going to occur at 8/5. Now, we have to get the y values for each of these. You're not going to use the derivative in this case. You got to use the original function. If I put 0 into here, 0 times anything is 0. So 0, 0 is our relative max. Now the relative min is not going to be that nice of a number here. 8/5 is going to have to go in for both the x's. Let's ignore this part here and just look at 3 and then 8/5 minus 4. If you do 8/5 minus 4 and then times 3, you're going to get this number. You're going to get negative 36 fifths for that part. But then you're going to have to do 8/5 raised to the 2/3. So you could leave your answer like that. You could also do a decimal on this as well. 8/5, the decimal equivalent of all this stuff should be negative 9.85 you'll get, so either one of those. Okay, so this would be the relative or local. Extrema would be these right here. Okay, now the other thing it's asking for is absolute extrema. Now on our sign chart here, we got the increasing and decreasing. Notice that on the end, let's look at what's happening on the end, because that's going to tell us what the graph does. On the end here, it's increasing from negative infinity all the way up to 0. So it's going from the bottom, always increasing. So it's coming from negative infinity, increasing all the way up till you get to the x value of 0. And then from here, from 8/5, it's increasing again all the way up to infinity. So on the endpoints, this is actually going to be going up to infinity and down negative infinity. Because of that, there's no cap, there's no highest or lowest number, because you have it's unbounded there. So what you would say here is you would say no absolute extrema. And again, it's basically because of these endpoints that we see there. If you took a look at the graph, you would see that's also the case as well. It's going to go up to infinity and down to negative infinity. Again, that's why there's no absolute extrema.